have the limit as h goes to 0 of f of x plus h minus f of x all over h. Well, because the other one is f prime of a, which is actually what I'm going to be doing here. By definition, a function f of x is differentiable at a if f prime of a is equal to, what is it? What's that definition? If it's differentiable at a point, the limit as x approaches a of f of a over x minus a. You have to know these two definitions down. So again, the first one gives you the general definition of a derivative on any point. You know what I mean? Anywhere. The second one is giving you the derivative at a certain point a. It could be 5, it could be 2, whatever. And when you actually solve it, you actually get the slope at that one point, only one point. Okay, and that's why I was saying for that question you asked. Okay, a function is differentiable if it is differentiable. I don't know, I'm spelling it wrong, I think. Differentiable on its entire domain. If this limit does not exist at a point, meaning from both sides, unless it's an endpoint, then the function is not differentiable. By the end, you'll be able to spell it at that point. This means if it's not differentiable at that point, there is no derivative there. For a function to be differentiable, it must be, it actually has to be continuous.
If you read the whole underneath.
Okay, so if you read the words underneath, it does say, in other words, differentiability implies continuity, but the reverse is not true, like we found in an example that we did in the last lesson. For instance, if I go to a corner like this, does everybody see this is continuous? I didn't lift my pencil, but at this point right here, it's not differentiable. Yes? I don't know what the slope is. It's some teetering on something or other. So this is huge. I have it so big because it's so huge. Differentiability implies continuity, but continuity does not imply differentiability. And I think using the absolute value function is the best thing. If I forget which one's which, I always remember the absolute value function. That's continuous. Everybody agrees. But at that point right there, because of that corner, it's not differentiable. So continuous, not necessarily differentiable, but differentiable means it has to be continuous. Okay, so what is differentiability? Exactly. Hey, look at that. We can say that a function is differentiable at a point if it is locally linear at that point. So what does that mean? If I zoom in to a curve or some function, do you know if you zoom in close enough, it starts to look like a line? Have you seen that? Like when you looked at these curves, if you just focus in on a certain point, it actually looks like a line. So that's what I mean by locally linear. If I zoom in to a certain section, it looks like a line. Okay? If it looks like a line, I can find the slope. Specifically, if the slope on the left of that point and the slope on the right of that point equal each other, then it's differentiable. So zooming in on the point of differentiation would show a straight line. Okay. So some examples where a function is non-differentiable. Does everybody see? The slope on the left of 0 is -1 slope. Yes? And the slope on the right is +1 slope. Therefore, at 0, it's not differentiable. So a corner is anytime you see a corner, you know on the graph it's not differentiable there. Here's what's called a cusp. When you basically have a curve going into another curve like that, kind of looks like a corner.
So corner equals no.
Corner equals no, a cusp equals no. Again, I'd be teetering. I don't know where to find the slope here. A vertical tangent, everybody know that a vertical line means there's no slope. So if you have no slope, how can you have a derivative? Makes sense? Yes? So something that kind of goes like that, that's a vertical tangent. A discontinuity, of course, that doesn't make sense, right? This is a slope of 0, this is a slope of 0. However, you're jumping. In order for it differentiability implies continuous. So if it's not continuous, then it can't be differentiable. But just because it's continuous doesn't mean it's not automatically differentiable. That's the thing, right? Differentiability implies continuity. This is always confusing. People don't understand the difference between the two. They say, oh, differentiability implies continuity. So if this is continuous, it must be differentiable. No. If it's differentiable, it has to be continuous. If it's continuous, then there's the prospect of being differentiable. Right? Okay. Show that this is differentiable. So so continuous doesn't mean it's differentiable. But well, that is true. That is true. But we're going to actually try by doing the left-hand derivative and the right-hand derivative, right? So, do you remember how to do this? And we're checking at a point. So which formula should I use? Yes. So I'm finding f prime of a, and I'm going to do the left-hand derivative. So, sorry, I'm not going to use a, I'm going to use 1. What am I doing? Does everybody see that? So because I'm coming from the left hand, this is going to be the limit as x goes to 1 from the left, which is a minus. So which function am I using here? I'm using the x squared, but we're putting it into the f prime a formula. So that is x squared minus 1 over x minus 1. Does everybody know what I'm doing? I'm using this formula. F prime of a equals the limit as x goes to a of f of x minus f of a divided by x minus a. So x squared was my f of x minus a. That was my 1. Okay. If I plug her in, I get 0 over 0. What did we learn from the last unit? We need to factor. So the limit as x goes to 1 of x minus 1, x plus 1 over x minus 1 means those cancel. And what is my slope then? 2. Yes? Because I'm trying to show that it's differentiable where
this is the limit as x goes to 1, so you plug in the 1.
But it's the limit of x goes to 1 from the left, so then you have to plug in the
well, the left is meaning I'm taking the left-hand function. Now I'm going to do it from the right. So the right-hand derivative is f prime of 1. The limit as x goes to 1 from the right. So which function am I using? 2x minus 1. So it's going to be 2x minus 1 subtract 1 over x minus 1, right? If I plug her in, I get 0 over 0. So if I simplify this, I get 2x minus 2 over x minus 1. If I plug her in, I still get 0, 0. Factor, yes, and I get 2 bracket x minus 1 over x minus 1. They cancel, and I get 2. Hey, they are the same. That means it is differentiable. Since left-hand derivative equals right-hand derivative, f of x is differentiable. So again, if I were to prove it's continuous, that doesn't mean it's going to be differentiable. It means I could quit once I found it wasn't continuous, but that still doesn't prove differentiability. So there was no point me showing it was continuous first, because I would have to do this step anyways, right? Does that make sense to you? So this way, if I go directly to differentiability, if it's not differentiable, then I'm done, right? Okay. So, okay, so this is this one here. So this is a cusp. Yes? Is it differentiable at 1? No. It's differentiable everywhere else. This is a cusp. Is it differentiable at 1? No, it's not. Again, there's a slope on the left and the right of 1. They're not the same. Coming to 1, it looks like a corner, but it's a cusp. Okay, let's do the next one. Okay, so does everybody see ABS on the calculator? You zoom in, you'll see it's a corner. Corner. Yeah, well, you can't. Okay, so let's punch this in. This is all practice in punching it in your calculator. As a power, I have to use brackets. So anyways, what is this? A corner, a cusp, a vertical tangent, or a discontinuity? Discontinuity. So if you have a discontinuity, automatically, what does that mean? Yeah, discontinuity means it's not continuous, but what does that mean? It's not differentiable, right? Okay. All right. So by logic, we're thinking the last one is a vertical tangent, but let's check with our graphing calculator. Okay, so this is a vertical tangent.
I mean, it's definitely vertical.
And if you ask yourself, like, listen, there might be a jump here, but ask yourself, is there anything that x can't be? It's a numerator. It's not a denominator, right? So, and actually, I see somebody using Desmos, and Desmos is beautiful in the fact that it's it doesn't have pixelation. No, you can't. No, you can't.